In section 1.1, we're going to talk about systems of linear equations, introduce what they are, and talk about solutions to those systems. A linear equation is an equation of the form a1x1 plus a2x2 plus a3x3 all the way to anxn equals b. In this case, the ai's, a1, a2, all the way to an, these are all constants, and the b is also a constant, whereas the x's are variables. When we're thinking about linear equations, we're often thinking about something of the form y equals mx plus b, a line. This is an equation of the form if we rewrite it. So if I move the x over to the other side, write it as minus mx plus y equals b, and instead I write x and y as the variables x1 and x2, I have minus m x1 plus x2 equals b. In this case, m is a constant, b is a constant, x1 and x2 are our variables. So anytime we're talking about a line y equals mx plus b, we could put it into this form. This form allows us to talk about more than just two variables. We could talk about three variables, and we can go even past that and go to n variables in a nice way. So let's look at some examples of linear equations. First one, 4x1 minus 5x2 plus 2 equals x1. In this case, what's a little bit odd is that I have two x1s, but I can get rid of that by combining like terms, moving the x1 over, and I can have 3x1 minus 5x2 plus 2 equals 0. And then to put it in the form in the definition, I can move the 2 over and have 3x1 minus 5x2 equals minus 2. In this other example, what's a little bit different is that I have some parentheses, but I can distribute that 2 to both terms, move all the x's to one side, and I can get something of the form in the definition. So here I have x2 equals 2 root 6 minus 2x1 plus x3. If I move all the x's to one side, I'm going to have 2x1 plus x2 plus x3 equals 2 root 6, something of the form that I have above. Remember, 2 root 6 is just a constant, even though it's in a square root, that doesn't make any difference. Let's look at examples of nonlinear equations. What doesn't work in these examples, the first one I have an x1 times an x2, and the other one I have a square root of x1. Both of those don't work. The square root of x1, remember that means the same thing as x1 to the 1/2 power. And for linear equations, I cannot have any power except for something to the first power. For the x1, x2, that's like saying something like x1 squared, except I have two different variables multiplied together. So in order for this to be a linear equation, I need to have all of my variables separate and to the first power multiplied by constants. Now that we've introduced what a linear equation is, we can start talking about a system of linear equations, or a linear system. This is going to be a collection of one or more equations involving the same set of variables, x1 to say xn, and commonly, if we're talking about 2 or 3 variables, we might have x, y, and z as our variables instead of x1 to xn. A solution to that system, the one or more sets of linear equations, is a set of numbers that satisfies each of those equations. We can think about those numbers as s1 to sn, and if we plug them in for x1 to xn respectively, they should satisfy each equation. When we're talking about solutions of linear equations, there are three possible things that could happen. You could have exactly one solution. That means consistent and unique. You could have infinitely many solutions, that is consistent and not unique, or you might have no solution, that being inconsistent. In this case, when we're talking about consistent, that word means that there is a solution. There exists at least one solution, maybe more. And unique is what defines if there's exactly one or more than one. So, to visualize solutions, the best thing to do is look at 2 and 3 variables, because we can draw lines in 2 and 3 variables, or draw linear equations in 2 and 3 variables. For lines, let's look at this first one. I have x1 plus x2 equals 10, negative x1 plus x2 equals 0. Remember that we could think about these as lines y equals mx plus b, just rewriting the variables and putting them in standard form. And if we graph those lines, we can see that their intersection point is exactly 1 point. So there is one unique solution. This is a consistent and unique system. You might have 2 lines that don't intersect at all. That would be when you have parallel lines. There's no intersection point, so there is no solution to that system. There's no point that you could plug in for x1 and x2 that would satisfy both of those equations. And you might have infinitely many solutions. In this case, you actually have the same line. These lines look different, x1 plus x2 equals 3 and negative 2x1 minus 2x2 equals negative 6, but they're really just multiples of each other. If you divided the second equation by negative 2 on both sides, you'd get the same equation back. So in this case, there are infinitely many solutions. Any point on that line satisfies both of those equations. Now this is just in 2 variables. Things become more interesting when you introduce a third variable, or in general, n variables. Let's think about this in 3 variables. The drawings get a little bit trickier because a linear equation in 3 space are planes, not lines. And we're thinking about how can planes intersect. But again, there's going to be 3 different options. You could have that the planes intersect at 1 point. That 1 point here is going to be right in the middle. That is a triple that you can plug into the system that satisfies all those equations. You might have that those planes intersect in 1 line. Any point on that line will satisfy those equations, so that is infinitely many solutions. Or you might have that those planes don't intersect at 1 point at all. Maybe you have some parallel planes, but they don't all have to be parallel. There's no point that satisfies all of those planes. So you could have no solution. We can't draw something in 4 space. That becomes much, much more complicated. But we're going to think about things with 4, 5, 6, and even more variables in this class. We're just going to do that abstractly. So what we're going to try to do is find the solution to different systems of linear equations, right? The solution set of a system is all of the possible solutions of a linear system. We just found that sometimes there's one unique solution, sometimes there are infinitely many. We want to try to find all of them. We are going to say that 2 linear systems are called equivalent systems if they have the same solution set. Sometimes we can rewrite a system and make it easier to write down, and since they have the same solution, we can just use the easier solution. So for instance, these 3 systems I wrote in example 4 all have the same solution, all have that same intersection point in common. And what we can do is, instead of using the complicated lines in the first example, we can use the horizontal and vertical lines to understand that solution perfectly. That solution is, we're often going to write solution SOLN, is the point 3, 2. Right? That's the same solution in the other 2, but we've just simplified it in some way to get down to this easier example. How we got down to that example is what we're going to talk about on the next few slides. There's different strategies we can use to get down to that easier example. Instead of dealing with equations, that gets very messy very quickly. We're going to use matrix notation. It's important to remember that a matrix is just a representation of the system. There's two different matrices we're going to think about. The first one is called the coefficient matrix. And the coefficient matrix just ignores everything on the right-hand side of the equal sign. And you look at the coefficients in front of the variables. We have a 1 there, a -1 there, the -2, and the +3. And those correspond to the 4 points in our matrix, the 4 entries in our matrix. Then you could have an augmented matrix. The augmented matrix is going to be the entire system, everything to the equal sign, and we often use a bar in the middle there to represent that equal sign. So this just has everything to the right of the equal sign there. Augmented means that you are adding something to the matrix, you're adding everything to the right of the equal sign. So what we did in this previous example is we took the augmented matrix, the system, and we simplified it in some way to get down to this final thing, x1 equals 3, x2 equals 2, which gave us a matrix that looks like this. And we're going to see in this class, when we have a matrix that looks like this, we are in a good position and we can finish the problem at that point. We have this nice diagonal of 1s. We have 0s everywhere else. That's what we're going to be looking for when we're going through these operations we're going to introduce in a second. All right, remember there are two different kinds of matrices. We're going to talk about both of them in this class. Coefficient matrix does not involve the equal sign. Augmented matrix does. So the operations that we're going to apply to matrices, or specifically rows in matrices, are going to be called elementary row operations. There's going to be 3 of them: replacement, interchange, and scaling. It's important to understand that when we are doing these operations on a row of a matrix is a linear equation. So we are doing something to a linear equation, or maybe more than one linear equation. So the first one is add one row to a multiple of another row. So what we're going to say is, to see the notation as well, we're going to take 2 rows, let's say row 1 and row 2, and we're going to add some constant. We'll use just a constant, let's say 4, row 1, we're going to add that to the other row, and we're going to replace that into a new row R2. Add one row to a multiple of another row. What this means when we're talking about linear equations, we're going to add 2 equations together, and that's going to give us a third equation out that's going to be easier to use, and you could always multiply some equation by some number. That multiplying some equation by some number is what we're going to call scaling. So for instance, you could have 4 R1 could be your new R1. When you're talking about a linear equation, what you're doing is you're just multiplying both sides of that equation by 4. So in this case, you would get 8x1 plus 4x2 equals 12. Now that's changing the equation, but it's still true because you multiplied both sides of that equation by that number. You could interchange 2 rows. Row 1 could switch with row 2. that doesn't change the system of linear equations. That's just changing the order that you're thinking about them in. But that's not going to change the system at all. And then again, back to the replacement thing. This is the one we're going to use the most. It's a little harder to understand. It's using this base thing that you can add two equations together and the equation will still be satisfied, kind of mixing in with this scaling operation as well. We'll see this in action in a little bit. All right, a definition here. We say two matrices are considered row equivalent matrices if one matrix can be transformed into the other matrix by a sequence of elementary row operations. This is going back to the previous idea that I can take one matrix and do some row operations and get a simpler matrix out, and these two matrices are equivalent matrices. They have the same solution. The same solution set, I should say. All right, and in fact here, if the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set, what I just said. So again, row equivalent matrices are gotten from each other by elementary row operations. Scaling one row, so multiplying it by some number, swapping two rows, interchanging two rows, or doing this replacement operation on rows. So let's look at an example. First off, we have a system of linear equations, three equations and three variables. And note that I don't have anything written here for x1 in the second equation. But that just means that this is a 0 x1. We're not going to write that down because it's not worth our time, but we have that 0 written in the augmented matrix. So when we're taking the original system, transforming it into the augmented matrix, we look at the coefficients 1, -2, 1, and 0, and those correspond to the 1, -2, 1, and 0, with the bar representing that equal sign. And we're doing that for all three equations. Now, normally when we work with matrices, once we put it into a matrix, we're not going to go back to the system until the very end. But just to show what's going on in this problem, this time we are going to show that. So let's look at the elementary row operations that we're doing to get from the top matrix down to the bottom matrix. So the first operation that we did here is we took 4 times the first row plus the third row, and that became our new third row. So in this problem, this first thing, we're not going to think about the second row at all. And note that the second row was left unchanged in all of that. Also note that the first row is left unchanged. That's because we're only replacing the third row. So the first row is left unchanged. Only the third row is changing. And what we're going to do is we're going to take 4 times the first row plus the third row. That gives us our new third row. The reason we're doing this is because I want to make this entry right here, this -4, I want this to be a 0. And the way that we can do that is if we take 4 times the first row, 4 times 1, and we add that to -4, that now becomes a 0. So let's go over some of these calculations real quick. If I take 4 times the first row, let's represent this row as 1, -2, 1, and 0. That's going to give me a 4, a minus 8, a 4, and still a 0. And I'm going to add that to that third row, minus 4, 5, 9, minus 9. And when we're talking about adding, we're just going to talk about term by term adding those rows together. That'll give us 4 minus 4 is 0. Minus 8 plus 5 is minus 3. 4 plus 9 is 13. And 0 minus 9 is minus 9. And that's exactly the row that we ended up with at the end. So that's what that replacement operation is doing. We're taking a multiple of one row, adding it to another, and then replacing that last row. We have more operations that we're doing, so let's look at the second thing. That was from this first system to that second system. From the second system to the third system, we are doing the scaling operation. We're taking 1/2 row 2 and replacing that with row 2. And that is looking at row 2 here only, and just halving all the numbers. 2 divided by 2 is 1, negative 8 divided by 2 is negative 4, 8 divided by 8 divided by 2 is 4. And the goal here was to get a 1 in that middle spot. All right, from the third to the fourth system here, what's done is another replacement. In this case, this was 3 row 2 plus row 3 is going to be our new row 3. And the goal is to get a 0 in that spot right there. And the same operation as we did before. 1 times 3 minus 3 is 0. 3 times minus 4 is minus 12, plus 13 is 1. And 3 times 4 is 12, minus 9 is 3. That gave us our 0, 0, 1, 3 right there. The next one down, what happened is that we wanted zeros here. So to do that, we're actually going to do 2 operations at the same time. We will do 4 times row 3 plus row 2 will give us our new row 2. That 4 comes from the opposite of that minus 4 right there. And we also at the same time did minus row 3 plus row 1 became our new row 1. That minus 1 coming from the opposite of that 1 right there. Going through those operations, and I think that you should take a minute, especially if you're not comfortable with this, and go through those operations carefully like we did for the first row operation right there to see how that's all working and see if you get the same numbers out. Finally, there's one more operation that we do here. The goal here is to get a 0 in that location. And that's going to be 2 row 2 plus row 1 gave us our new row 1. We'll talk about why we chose those operations, why we wanted zeros in those spots. But now that we can see we have a solution to the system, x1 equals 29, x2 equals 16, and x3 equals 3. That is a point 29, 16, 3 in 3 space, and that satisfies the original equation. This also tells us that there is exactly one unique solution to this equation. Right? we can check that that solution is indeed a solution to the original system by plugging it in. Right? We're going to plug in 29 into x1. We're going to plug in 16 to x2. And we're going to plug in 3 into x3. So our original system, we plug in those values, everything comes out and all of these equations are satisfied, which means that that is indeed a solution to the original system. It's important to remember when we're dealing with matrices to sometimes bring yourself back to equations and remind yourself what you're working with. Equations and things we can plug into equations. All right, there are two fundamental questions that we're going to ask in this course: existence and uniqueness. Okay, the first one is the system consistent? Does a solution exist? Is the system consistent? Does the solution exist? And then, if it exists, is it unique? Is there one and only one solution? This is going to be what type of the solutions do we have? Consistent and unique, consistent and not unique, inconsistent. One solution, infinitely many solutions, no solutions. So let's look at some examples. First example here, is the previous system consistent? All right, the previous system that we worked with, we can see not from the very end we knew it was consistent, but even just halfway down, we got to this part right here. And at this point, we can actually say that this is consistent and unique. And the reason that we can do that is because we have this thing in triangular form. This triangular form, looking at that triangle right there, we have zeros everywhere underneath this diagonal, and that diagonal has non-zero entries. Okay, it doesn't have to be one necessarily. This has to be non-zero entries and then zeros everywhere else. If we see that, that means that we have a consistent and unique solution. And let's look at why that's the case. The reason why this is going to be the case is by something called back substitution. Back substitution, we have our three equations here. And we can start with the nice, easy equation, x3 equals 3. We can plug that into the previous one and get an answer for x2 out. So we can plug in x3 equals 3 into x2 minus 4x3 equals 4. And that'll give us x2 minus 4 times 3 equals 4, or x2 equals 16. Then I can plug x2 equals 16 and x3 equals 3 into the first equation, x1 minus 2x2 plus x3 equals 0, which will give us x1 minus 2 times 16 plus 3 will give us a 29. So as long as we have this triangular form that I can start with x3 equals some number, I can plug that into the previous equation, get x2 equals number, plug that into the first equation and get x1 equals some number, and I can do that as long as I have zeros underneath that diagonal and I have non-zero entries here. These don't have to be ones, they have to be non-zero. That is our triangular form that we're looking at. Okay, to say that carefully, the triangular form means that I have zeros underneath the diagonal, and then on the diagonal, as big as that diagonal is, these are non-zero entries. Ones are nice, but they don't have to be ones. All right, so new example. Is the following system consistent? We have the system given by 3 equations here, and when we're going to be working this, we're always going to bring it into the augmented matrix. So it's good to take a second, go through this example, and make sure you understand where these coefficients are coming from to get this new matrix. The goal is to try to put it into triangular form. That is, we want to have zeros below the diagonal and ones on the diagonal. To do that, the first thing that we need to do is to get a non-zero entry in that top left corner. Right now it is 0. That's not good. So to do that, we can switch row 1 and row 2. Right, we're just changing the order of the equations that were given. Then what I want is I want zeros underneath that first diagonal entry. I already have a 0 in that second one, so I really just want a 0 in that third one. To get rid of that, we're going to take the opposite of it, -5, multiply that by the first row, add it to the row that we want, and then replace that into the new row 3. If you take -5 times 1 plus 5, you'll get a 0 in that spot. If you take -5 times -2, multiply that, or add that to 3, you get negative. If you take the -5 times -2, add the -7, you'll get a 3. 3 times -5 is -15, plus 9 is -6, -1 times -5 is 5, plus 0 is 5. That's where we get our new 0, 3, -6, 5 row in row 3. Then what I want to get triangular form is I want to have a 0 in that spot underneath the diagonal. I have a non-zero in the diagonal. I want a 0 underneath it. So to do that, I can do row 2 plus row 3 is our new row 3. I forgot a little minus sign before, so there's a little minus sign of that 3 in the diagonal. If I add those together, I'll get a 0 in row 3. But what happens there, I get a -6 plus. All right, and I apologize. I should have had a +3 in that first system. So everything should be +3. And then when I get down to the very end, the row operation that I want is minus row 2 plus row 3 is my new row 3. -3 plus 3 is 0. Minus -6 plus -6 is 0. And -8 plus 5 is -3. Now the problem with this last row is the equation that gives us is 0x3 equals -3. And that is never true. There is no value that you can plug in for x3 that if you multiply it by 0 will get you -3. So that's going to be inconsistent solution. There is no solution. So when you're working with a matrix, what you're looking for is this 0 on the left-hand side of that bar, and then some non-zero value on the right-hand side of that bar. All right, we're going to have no solution if I have a row that is zeros and then some non-zero number here. That'll be an equation that we can never solve. Last example here, going to be a little bit different. We're going to be given a system. We're going to say that h is some value, and I want to find for what values of h will the following system be consistent. So I'm going to go through and try to get this triangular form, going through row operations, and then think about this no solution thing that I just came up with. So the original system, putting it into a matrix, is 3 minus 9 with the bar, 4 minus 2, 6 with the bar, h. And I'm going to go through all of this algebra with h just staying in there. So the first operation that I want is I want to get a 1 in this location right here. So to do that, I'm going to do 1/3 row 1 is going to be my new row 1. 1/3 times 3 is 1. 1/3 times -9 is -3. 1/3 times 4 is 4/3. It's going to be important that we don't get too scared of fractions in this class. So sometimes they're just going to pop up and we just have to deal with them. And we're going to have to do that early and often. The next thing that I want to do is I want to get a 0 in that spot right there. To do that, I can take the opposite of it, 2. And since I have a 1 in that top spot, I can go 2 row 1 plus row 2 is going to be my new row 2. 2 times 1 plus -2 is 0. 2 times -3 is -6. Plus 6 is 0. And 2 times 4/3 is 8/3. Plus h is h plus 8/3. Note that you could have done this in one step if you didn't want to get a 1 in that first spot. So you could have gone from here to here in one step, but you would have to do a more complicated row operation. You'd have to take something plus row 1 plus row 3 to go into row 3. But what has to be that constant out in front would have to be 2/3 row 1 plus row 3 into row 3. That's doable, but it just be a little more complicated. Either way that we do it, we get this final thing with a 0, 0, and h plus 8/3 on the other side. In order for that to be a consistent solution, in order for it to have a solution, we need h plus 8/3 to be equal to 0. Or in this case, h equal to -8/3. That's the only way that we're going to have a consistent solution there. Now what this also means that there's actually going to be infinitely many solutions. We're going to talk about that in a later section. But we do have a solution. If this were anything but 0 on the right-hand side, it would be inconsistent.